Hi everybody, this is Justin with Top Tier Math, and we're going to cover an Algebra 1 final, and in particular the January 2020 Regents exam for Algebra 1. Now this is the New York State exam. It's one of the most comprehensive ones that I've come across, and I use it with a lot of my students. And basically the setup for the videos is this. One, do the exam. So I posted a link in the description. Make sure you do the exam and see which ones that you've missed. I've also posted a link to the answers so you can check yourself and see which ones you got wrong. And when you're not sure why you got it wrong, because it'll tell you what the answer is, you come back and watch me and we'll work through the actual solutions to the problems. And I've put some timestamps for each question in the description so you can skip ahead to whichever ones you missed. This video covers questions 1 through 9, part 2 covers 10 through 18, and part 3 covers 19 through 24. And next to some of the timestamp, I provided the link to some free extra practice problems for you to work on just to make sure you're solid in every single area of Algebra 1 and ready for your final. Now that should cover it, so let's go ahead and get started. When I take a look at number 1, I see a function notation problem that's basically asking us what is f when x is equal to 2? That's exactly what this means. What is the value of this function when x is equal to 2? So all you have to do is take that function, and everywhere that you see an x, I only see one here, 3 raised to the x, all you have to do is take the 2 and replace every single x with that. Substitute that in for x. And then evaluate your function. So here we'll do exponents first. This is just going off of order of operations. And we take 2 times 9, that's a 2. And then we add 1. 2 times 9 gives us 18. 18 plus 1 is 19. And that's how we get that. So number 1 is purely just testing how comfortable are you with function notation, evaluating functions, and a little bit of order of operations at the end. Number 2 is an example of exponential decay, and we have to write an equation that represents what's going on in this situation. So I've written the problem down here, or the equation down here. You definitely need to remember this. You have to remember this. You're going to see it again. What the A represents is the initial value, R is the rate of decay, and X is just how many times it's decaying. So if we apply this formula to the problem, it looks like after every round, 1/2 of the players are eliminated. So if I go ahead and plug that in, we know R is equal to 0.5. And the initial amount that we start with, we start with 64 players. And then this is happening 3 times. We're going through 3 rounds of this. So we plug that in. So if we go back and plug all our values in, it looks like 1 is the only one that makes any sense. I'm starting with 64 players. I'm losing 1/2 after every round, and I'm going through 3 rounds. So again, this exponential decay formula you've got to memorize because you will see it again. For number 3, we're being asked to find which number is not in the solution set. What we need to do first is actually solve this inequality so that we know what the actual solution set is. So let's go ahead and do that. If I solve this, I'm just going to write it out. Nope, not equals. Greater than or equal to 58. All you would do is subtract 2 on both sides. We get 56 is greater than or equal to 7x. Divide by 7. And we get x is greater than or equal to 8. Now, we have to find out which one of these answer choices does not fit that. X is greater than or equal to 8. 10 works, 12 works, 8 works because 8 is greater than or equal to itself. 6 does not work. 6 is not greater than or equal to 8, so 6 would be our answer. So number 4 is asking us which of these tables could represent a function. If all I want you to remember for this is a function basically tells us that for every single input, we only get one output. And if you remember, right here, we're given x and f of x. X is the input, f of x is the output. So if you look at we'll start with number 1. Number 1, if I have x is 1, my output is 4. If x is 2, my output is 2. But down here, look, I get the same x value, so my same input is giving me a different output. So I'm getting 2 different outputs for one input. That can't be a function. For number 3, answer choice 3, I have, if you look and you see here, I've got 2 of the same inputs, again, giving me different outputs. That's not a function. Cannot be a function. If you look at number 2, 1, 2, 3, 4, we've got 4 different inputs, so there's no problem there. That could be a function. And then just to make sure, answer choice 4, I see 3 being repeated twice as an input, but it's giving me 2 different outputs. Again, that cannot be a function. If it's a function, every single input should only give you one output. Otherwise, it's not a function. So if you look at this one, we've got a whole bunch of fractions going on, but we're just basically trying to figure out what is our value of x that makes this true, aka what is the solution. So there's a couple different ways that we could go about this. Personally, what I like to do, and when we have multiple different denominators, is I like to multiply by whatever the least common multiple is of those denominators. In this case, 4, 3, and 12, their least common multiple is 12. So I'm going to multiply both sides, basically the entire equation, by 12. And I'm going to show you it's actually kind of nice. So we're going to use the distributive property here. So 12 times this, there would be a 12 over 4. That's basically a 3. So I'm going to write our answer, or our new equation over here. There's a 3 up top times x minus 3. 12 times 2/3. Well, again, the 12 and the 3 cancel each other out to a 4. So 4 times 2. And then equals, so if you look, 12 times 12 on the bottom, the 12s just cancel each other out automatically, and we're just left with the 17. So that is really convenient. Equals 17 equals, and then now this just looks like a normal linear equation that we solved before. So let's distribute this 3. We would get 3x minus 9 plus 8 equals 17. Minus 9 plus 8, that's just minus 1. My handwriting is getting progressively worse as we move further down. So 3x, we'll add 1 to both sides. We get 3x equals 18. Divide, that's an 18. And then divide everything by 3, and we get x equals 6. Now let's go back and see which one of those is our answer. It looks like number 2. X equals 6. And you could, if you want, one good test-taking strategy is to plug in the values, because if it's multiple choice, you can plug them in. But this one would actually probably not necessarily take longer, but if this is calculator inactive, it's not going to be very fun for you. So I do want you to know that technique that we do. I like to multiply by the least common multiple. You get rid of all the fractions. You don't even have to worry about them anymore. It makes the whole equation a lot easier to solve. Now, number 6 looks like so much fun, but basically all I want you to look at here to start is if we're trying to write an equivalent expression, I look at here and I say, what factors do they share in common? 18x squared and negative 50, they both share a 2 in common. So I'm going to go ahead and factor out a 2, and what we're left with is 9x squared minus 25. Now right here, it might not even be so obvious, but if you notice, this is actually your difference of squares that we can use here. A squared minus b squared. And I'm going to write that up here just so you guys remember. You do have to remember this 100%. It will pop up. A squared minus b squared, that factors to a minus b times a plus b. So if you look, 9x squared, that's just 3x quantity squared. 25, that's just 5 quantity squared. So we've got our a and we've got our b. Let's go ahead and put them in their own binomials using this difference of squares technique up here. So we've still got a 2 on the outside. I'm going to change the colors a bit. We've still got a 2 on the outside. The first one is 3x minus 5. The second binomial is 3x plus 5. And that's it. So let's go and see which one of those makes the most sense. I see that looks just like number 3. All of these look like they could be possible answer choices because the question itself is kind of funky, but it's a difference of squares that only shows up after you factor out a 2. So be careful of those. If you look at this and you think, can that be difference of squares? Sometimes you have to pull something out first. You need to factor something out, and then you get a difference of squares that you can factor using that special technique. Okay, so just be careful with those ones. These ones look wild. So hopefully this one fits on the screen. It's kind of a long problem. It's like just very, very tall. But basically, all I want you to remember for this one is if you look, we're starting with f of x. They tell us what that is. And they're trying to figure out, okay, well, if we add some k to that, how do I go from there to g of x? So if you look at this distance. I'm going to put this in red. We move down how many units? We move down 2 units. What I want you to think of vertically is that's a movement downward of 2. That's minus 2. So we would have to do f of x plus negative 2. It would really just be f of x minus 2. So plus negative 2, minus 2, those are the same things. That's why our answer would be 4 for that one. We shifted this whole f of x down 2 units. That's why we subtracted 2 from it. Okay, so that's function transformations. If that's not so obvious or you're not comfortable with that, definitely go back and take a look at some practice problems with function transformations. Okay, so I'm not gonna lie. At first glance, this problem looks absolutely ridiculous. It reminds me of problems that gave me nightmares when I was in algebra. So let's go through this one. First things first, I want you to see if you can identify what the pattern is. So if you take a look, what's happening, one, I want you to notice that this 4 square in the middle is not changing. So we're not adding anything to that middle block of 4 squares. What's happening is every single time, we're just adding a block to the 4 corners. So if you notice, and again, to go from figure 2 to figure 3, we're just adding another block. So each of these diagonals, it goes from 2 to length 3 to length 4. So, and since we're adding 4, 1 to every corner, we're adding 4 every single time. So to go to figure 2, we had to add 4 to the original, and then we have to add 4. And then you can imagine, to go to figure 4, we would add another 4. So what you have to do here is figure out, okay, if I'm trying to figure out how many are in figure 35, what helps is, okay, well, let's see how many are in figure 1, how many shaded blocks are in figure 1, and you and I know that every single time we move to the next figure, we're adding 4. So what's happening is, to go to figure 1 to figure 35, that's a change if you want to think of it like that. We're adding 34 more figures, right? And remember, every single time we add a figure, we're adding 4 blocks. So if I'm changing, let me move this down here. If I'm changing 4 34 times, what does that give us? How much is this? 4 times 34, that gives us 136? 136. That's how much we've changed after we've gone from figure 1 to figure 35. Now you and I, we have to add the initial amount that we already had. So what was this? 4, 5, 6, 7, 8, 9, 10, 11, 12 shaded blocks in the beginning. We have to add those to figure out how many total shaded blocks they will be in the 35th figure, and that gives us 148. Okay, so that's why we get number 2 for this one. So it's all about figuring out what the pattern is. How many times am I doing that pattern? In this case, we were doing that pattern from 1 to 35. That's a change of 34 figures. So 34, that's why we did 34 times 4. And then we had to add the initial value back. It's actually very, very similar to the linear equations that you've been doing. We actually could model it with a linear equation where our slope is 4 and we're changing 34 times. And then we add our y-intercept, if you want to think of it like that. If that's too much, then don't worry about that. But basically figure out what the pattern is. How many times are we doing that pattern? So we did it 34 times, and then add the initial back in this case. But I can definitely see why 3 and 4 would be tempting solutions, but our answer would be number 2 for this one. Okay, so in this particular problem, they're asking us to find the zeros of the function. I went ahead and wrote these 3 different words up here: zeros, roots, and x-intercepts. They all mean exactly the same thing. So you will see them. I want you to be comfortable with what they mean. They're all synonymous. So what's happening here is, if I want to find the zeros or the roots, the x-intercepts of a function, I'm taking that function, x cubed minus 9x squared in this case, and I'm setting it equal to 0. That's what that means. That's really why we call it zeros. What I want you to do from this point, I want you to be able to see, a lot of people might want to bring the 9x squared to the right side. Don't do that. What we want to see is, what can I factor out of these two terms? What's the greatest factor that they share in common? And it just so happens that it's an x squared. So if I factor out an x squared, the x cubed just becomes an x. The minus 9x squared just becomes a minus 9. And then if you look down here, all you have to do with this is, I would put this in parentheses. You don't have to, but it looks just like what you used to do back when you would factor problems, and then you would set them equal to 0. We're doing the same thing here. Set x squared equal to 0. Set x minus 9 equal to 0. X squared equals 0. That's just 0. So x equals 0 for that. X minus 9, I would just add 9 to both sides, and I would get x equals 9. So let's double check up here and see which one of those makes sense. It looks like that would be number 2 for this one. So again, all we're doing here is looking for the common factor and saying, all right, because you look and you say, well, it's a cubic, like how do we solve that? But all you have to do is figure out what the common factor is, factor that out, and then set each of the expressions equal to 0 and solve for x. And those will give you your zeros, your roots, your x-intercepts, all the same thing.